Yeah.
Shall I start, sir? Vijay sir and Anbalagan sir, shall I start?
Noise coming, disturbance coming.
Very good morning to everybody. Today we are gathered here for the witness of public viva's examination for TV Sridevi on the topic investigation of transition metal chalcogenides for photocatalytic activities and microbial growth inhibition. I welcome to my head of the department and my dear colleagues and professors from the various institutions and research scholar and UNOM besties for today program. Today we have here Dr. N. Vijayan, Principal Scientist and Associate Professor, CSIR NPL, New Delhi, as our external examiner. I would like to say a few words about examiner. He awarded PhD in Anna University. He joined CSIR NPL on 2004 as a scientist, and he is serving as an associate editor for Asian Journal of Physics and Journal of Functional Material and Biomolecules. And also he received prestigious CSIR Young Scientist Award on 2007, and he received the Bharat Excellence Award on 2014 and the Best Innovative Researcher Award on 2015. So his citation score is 4,500 and above, and also he guided 4 scholars and guiding 6 scholars presently. Sir, I welcome Dr. N. Vijayan for the scientific forum. Welcome, sir. And also I thank for accepting my request as a thesis evaluator. And also I am very much happy to welcoming Dr. G. Anbalagan, Professor, Department of Nuclear Physics, University of Madras, Chennai, for our external examiner. Few words about Dr. Anbalagan, sir. Total citation of the publication is 2,100 and above, and he is lifetime member for various associations like Indian Spectroscopy and Indian Physics Association and Indian Crystal Growth Association. He received a project from various funding agencies like DST SERP, MHRD STARS, and also RUSA funding. The number of PhD scholar awarded 10, and presently he guiding 8 students. And also he is serving as extension activities like coordinator, Physics Olympia 2018 and 19, arranged by Academy of Science for CSIR and NET examination. He stimulated the research thirsty for the various colleges all over India through summer training program for MSc students. And also he is the university nominee and a subject expert in many colleges. I welcome sir, Professor Dr. Anbalagan sir, and also I thank for accepting as a Viva examiner. And also I am welcoming Professor Dr. M. Kandasamy, my mentor, such an inspiration and a backbone of my career. And also I am welcoming Professor V. Narayanan for the role model. And also I am welcoming Professor Ravichandran and Professor E. Murugan and also Professor A.K. Monakrishnan and Professor Pandian for this scientific occasion. So regarding the scholar, she registered the PhD on January 2017 and she published 3 papers from her research work.
Sir.
Material science and in semiconductor processing, AIP advances, materials today proceedings. She attended national and international conferences and she get the best paper award on ICRA conference and also best oral presentation award NCAFM conference. So with this introduction, I hand over the session to the examiner to conduct the public viva's examination and declare the result. Sir, Vijayan sir and Anbalagan sir.
Yes, yes.
Please take.
Good morning to one and all present here. I think Professor Vijayan is on the line. So the candidate can present her work for 30 to 35 minutes, followed by the interaction with the examiners, as well as the professors and scholars who are in the online meeting, online Viva examination, and the questions raised by the examiners who have evaluated the thesis. Then finally, we will conclude the Viva examination session. So, with the permission of Mr. Professor Jayan, now I request the candidate to present her work for 30 to 35 minutes. Jain sir. Sridevi, my voice is audible.
Yes, sir. Your voice is audible. I'm getting your voice.
We will start and we will inform to.
Okay, sir. Okay.
Your Vijayan sir.
Okay.
Okay.
Sir, good morning, sir. I joined, sir. Joined.
Sir, good morning. Good morning. How are you,
Yes,
sir?
sir. Yes, sir. Yes, sir. How are you, sir? Nalla irkingla?
I am fine. I'm fine. Nalla irukken.
Yes, sir. Yes, sir. Yes, sir.
Okay. Okay.
Yes, sir. Yes, sir. Yeah. We can start, sir. We can start.
Yes. Yes. Okay.
Devi, you can start.
Okay. Good morning to all. I'm D.V. Sridevi, full-time research scholar. I'm working under the guidance of Dr. E. Sundaravadivel, Assistant Professor of Department of Chemistry, SRM Institute of Science and Technology,
Make it full screen.
Katamuruthu.
Make it full screen.
Good morning to all. I'm D.V. Sridevi, full-time research scholar. I'm doing my PhD under the guidance of Dr. E. Sundaravadivel, Assistant Professor of Department of Chemistry, SRM Institute of Science and Technology, Katamuruthu. My thesis title is Investigation on Transition Metal Chalcogenides and Oxides for Photocatalytic Activities and Microbial Growth Inhibition. Overview of my present thesis: Chapter 1, Introduction; Chapter 2, Experimental Method; Chapter 3, Structural, Physicochemical and Biological Properties of Pure overview of my present thesis: Chapter 1, Introduction; Chapter 2, Experimental Method; Chapter 3, Structural, Physicochemical and Biological Properties of Pure Fe-doped and cadmium selenide nanoparticles.
Please, you can make a full screen. When
Sir,
zooming
if I
nearby,
make,
one logo is there, right? You can
Sir,
click
I
on
make
that.
full screen.
Yeah, come down, come down. When you zooming nearby, zooming, one logo is there at the last end. Or else put Control F5.
Now it's okay, sir. Overview of my present thesis: Chapter 1, Introduction; Chapter 2, Experimental Methods; Chapter 3, Structural, Physicochemical and Biological Properties of Pure and Fe-doped cadmium selenide nanoparticles; Chapter 4, Synthesis and Characterization of manganese-doped zinc selenide nanoparticles for photocatalytic activities and biological application; Chapter 5, Synthesis of pH-dependent TiO2 nanoparticles for bacterial growth inhibition and osteoblast proliferation; Chapter 6, Conclusion and future work. Chapter 1, Introduction. Chalcogenides semiconductor materials recently used in worldwide because of new technologies and engineers and technological advisors in the field of science and technology. It describes information regarding preferred properties and prominent applications such as solar cells, spintronics, optoelectronic devices, photocatalytic activity, and biological application. Among these, I have done photocatalytic activity and biological application for my research work. Different groups in the modern periodic table have been combined and created groups forming binary and ternary semiconductor materials. Herein, different studies have been made on doped cadmium selenide, zinc selenide in the presence of transition metal ions. Cadmium selenide is an inorganic compound of formula CDSE. Is a N-type semiconductor material which exhibit either the Woodside-like hexagonal structure or zinc blende-like cubic structure. The general properties of cadmium selenide: black, translucent crystal, and odorless. Its band gap value is found to be 1.74 electron volt. The material can be doped with N-type doping. P-type doping is more difficult. Therefore, much of the researchers can be synthesized cadmium selenide for research activities. Likewise, cadmium selenide, zinc selenide is also a N-type semiconductor materials, can be made in both hexagonal and cubic crystal structure. Its band gap value is found to be 2.7 electron volt. Besides chalcogenides semiconductor materials, various known metal oxide semiconductors such as titanium dioxide, zinc oxide, cadmium oxide are widely used because of widely used in many applications. They are solar cells, sensors, electronic, environmental remediation due to its super hydrophilic property. Among these applications, photocatalysis is considered to be the most practical due to its usage of sunlight to decompose organic pollutant. Additionally, some of the parameters such as temperature, pH, chelating ligand is required for to promote phase selectivity. So here pH is an important role on TiO2 nanoparticles, which enhance the photocatalytic activity and prompted a lot of interest in medical sector. Generally, TiO2 structure exhibit in 3 different polymorphs. They are anatase, bruchite, and rutile. Therefore, biphasic TiO2 with either anatase bruchite or anatase rutile mixture has the potential to become the better heterogeneous photocatalyst than pure anatase due to the enhanced charge carrier separation, so that it has been widely used in solar cells and photocatalysis. Chalcogenides semiconductor materials are recently used because of its wide band gap value and good electrical magnetic properties, high mechanical and thermal stability, and enhanced photocatalytic activity, which in turn make them suitable for many applications. This slide, you can see the synthesis approaches of doped nanoparticles can be characterized into 2 methods. One is wet chemical method, another one is the dry method. Wet chemical method involves chemical co-precipitation, salt gel, hydrothermal, sonochemical, microemulsion, and microwave synthesis. Dry method, which involves chemical vapor deposition, spray pyrolysis, structuring, thermal decomposition, vapor phase oxidation. Among these, I have done wet chemical method, like a chemical co-precipitation, salt gel method, and hydrothermal method. Each method has some advantages and limitations. The advantages of chemical co-precipitation methods: low cost method and environmentally friendly. Then no temperature, pressure not required. The disadvantages of chemical co-precipitation method: sludge are formed. Extra amount are required for the disposal of sludge. The advantages of salt gel method is also simple and economic method. The drawbacks of this salt gel method: avoiding the agglomeration and controlling the growth of particles. Then the advantages of hydrothermal method: high production efficiency and environmental friendly. The drawback of this method: it requires high temperature and pressure. These are the literature survey of cadmium selenide, zinc selenide, and the titanium dioxide nanoparticles. From the literature survey, I found that cadmium selenide, zinc selenide, and titanium dioxide already have been used for many applications. So I tried different applications by doing photocatalytic efficiency and biological activities. Objective of thesis: to prepare cadmium selenide and Fe-doped cadmium selenide nanoparticles by varying dopant concentrations such as 5, 10, and 15% via chemical co-precipitation method. to study structural, optical, and magnetic properties of these materials will be characterized by using various techniques. The photocatalytic activities towards methylene blue dye under visible light for all the samples was determined. In addition, the cytotoxicity on breast cancer cell lines was also investigated in this chapter. In chapter 4, to prepare zinc selenide and manganese doped zinc selenide nanoparticles at various dopant concentrations such as 5, 10, and 15% by hydrothermal route, the structural, optical, and magnetic properties of these materials will be characterized by some of the techniques. The photocatalytic activity towards the reactive black dye under visible region and also the cytotoxicity on lung cancer cell lines was also investigated. In chapter 5, to synthesize titanium dioxide nanoparticles by varying pH levels such as 6, 8, and 10 by sol-gel method. To perform characterization studies like powder XRD, FTIR, UV, HRTM, micro-Raman, and PL studies to confirm as synthesized samples. To perform photocatalytic application for environmental remediation and to check the bacterial growth inhibition, also the toxicity to the mouse mesenchymal cells by BRDSA. Chapter 2, materials and method. These are the different techniques I used my research work. They are powder XRD, Raman spectra, transmission electron microscopy, EDAX, FTIR spectroscopy, UV visible thermal analysis, and VSL. This is a general photocatalytic mechanism. When the light is passed through the semiconductor materials, when the electrons in the valence band get promoted to the conduction band by leaving holes in the valence band. The excess of electrons in the conduction band may react with the oxygen, dissolved oxygen forms oxygen radicals. The holes in the valence band may react with the water molecules forms a hydroxyl radical. As a result, the electron are transferred on the dye molecule to the adsorbed synthesized nanoparticles. Chapter 3, structural, physicochemical, and biological properties of pure cadmium selenide and Fe doped cadmium selenide nanoparticles. This is a general synthesis procedure for the cadmium selenide and Fe doped cadmium selenide nanoparticles by chemical co-precipitation method. Initially, 0.3 ml of mercaptan was added to the sodium selenide solution to avoid the agglomeration of nanoparticles during the synthesis procedure. Then to this 4.3 gram of cadmium acetate was added drop by drop with the constant stirring. The red precipitate of cadmium selenide get precipitated, then it's centrifuged and washed several times using methanol and water. The procedure followed was same as in the synthesis of cadmium selenide, and appropriate amount of FeCl3 dissolved in cadmium acetate. Result and discussion. This is a powder X-ray diffraction pattern of a pure and Fe doped cadmium selenide nanoparticles. It shows cubic phase as parasitic peaks located at 25.3, 42.1, and 49.7, corresponding plane of 111, 220, 311 respectively. This experimental data matched with the JCPDS code number 190191. Broadening of peaks is obtained in this powder XRD pattern shows all the synthesized nanoparticles exhibit amorphous in nature. In addition, the crystallite size of the synthesized nanoparticles was found to be 1 to 4 nanometer, which is confirmed by the Scarrel formula. This slide shows 10 images of a cadmium selenide and Fe doped cadmium selenide nanoparticles. Figure A shows transmission electron microscopy images. It shows clear spherical and non-homogeneous structure. Figure B shows SAD, that's selected area of electron diffraction pattern, shows fine circular rings representing all the synthesized nanoparticles exhibit amorphous in nature, which is well agreement with the powder XRD data. Then figure C shows a TEM EDAX analysis, which confirms the presence of elements such as cadmium, selenium, and iron, and to know its weight percentage of its composition. This slide shows the spectroscopic analysis of synthesized nanoparticles. Figure A shows FTIR spectra of cadmium selenide and Fe doped cadmium selenide nanoparticles. Generally, FTIR spectroscopy is used to determine the functional group of synthesized nanoparticles. The peak at 733 centimeter power of -1 was assigned to the cadmium selenide stretching mode of vibration. Then the broad band at 3401 to 3411 centimeter power of -1 was due to the OS group of vibration. Then the peak at 1640 centimeter power of -1 was due to the C double bond of a stretching mode of vibration. Figure B shows the FT Raman spectra of cadmium selenide and Fe doped cadmium selenide nanoparticles. FT Raman spectroscopy is used to quantify the vibration phonon mode of synthesized nanoparticles. Raman peak at 205 and 409 centimeter power of -1 was assigned to the one longitudinal and two longitudinal optical phonon mode of cadmium selenide nanoparticles. And the characteristic peak at 134 centimeter power of -1 was due to the second transverse acoustic phonon mode of undoped cadmium selenide nanoparticles. Then the peak at 251 centimeter power of -1 was due to the Fe at cadmium selenide nanoparticles, one longitudinal optical phonon mode of Fe at CDSC nanoparticles. Figure C shows the UV absorbance spectra of cadmium selenide and Fe doped cadmium selenide nanoparticles. It shows absorption peaks of Fe metal doped into the cadmium selenide nanoparticles. We shift towards the higher wavelength region due to the quantum confinement effect. It's reliable for redshift. Then figure D shows band gap determination of cadmium selenide and Fe doped cadmium selenide nanoparticles. The band gap values were found to be 2.15 electron volt for CDSC, 2.02, 1.88, and 1.79 electron volt for Fe doped cadmium selenide nanoparticles, which shows the band gap values was decreases with increase of crystal size. This slide shows TGA, DTA, and DSC curves for cadmium selenide and Fe metal doped cadmium selenide nanoparticles. Generally, the thermal stability and physical chemical properties of synthesized nanoparticles can be characterized by TGA, DTA, and DSC curves. The last mass from 10 to 20% of last mass was observed at 400 degree centigrade was due to the removal of water molecules on the surface of the synthesized nanoparticles. The second mass loss, that is 10 to 30% of last mass was observed above 400 degree centigrade. This due to the collapse of the cubic crystal structure. That's exothermic peaks, collapse of the cubic crystal structure. Then the peak above 800 degree centigrade, the third mass loss was observed due to the endothermic peak. Last mass was associated with the sublimation reaction. This slide shows vibrating sample magnetometer of synthesized nanoparticles. Generally, the pure cadmium selenide nanoparticles exhibit a diamagnetic with a negative susceptibility value, but we made top-down approach. It cannot remain diamagnetic. They exhibit either paramagnetic or ferromagnetic behavior. As a result, the saturation magnetization values was increases by increase of Fe metal doped into the cadmium selenide nanoparticles. This result or agreement with the already reported work. This slide shows the UV absorbance spectra of methylene blue dye. When the visible light are irradiated to the cadmium selenide nanoparticles from 0 minutes to the 150 minutes, at the time interval of every 30 minutes, the degradation intensity of the absorbance decreases with an increase in irradiation time. The maximum absorption wavelength for the methylene blue dye was found to be in the range of 667 nanometer. The degradation efficiency of methylene blue dye was 57% for cadmium selenide, 68%, 71, 79% for Fe metal doped cadmium selenide nanoparticles. As a result, 15% of Fe metal doped into the cadmium selenide nanoparticles showed enhanced photocatalytic activity when compared to the pure cadmium selenide, which is confirmed by plotting C by C naught versus time in minute power of -1 as shown in figure A. Then figure B shows a kinetic plot of cadmium selenide and Fe doped cadmium selenide nanoparticles. The straight line degradation emphasizes all the synthesized nanoparticles exhibit pseudo first order kinetics. The rate constant values for cadmium selenide is found to be 0.0136 minute power of -1 and 0.0176, 0.0212, 0.0207 minute power of -1 for 5, 10, and 15% of Fe doped cadmium selenide nanoparticles. This slide, you can see that in vitro cytotoxicity of cadmium selenide and Fe doped cadmium selenide nanoparticles on MCF7 breast cancer cell lines. Initially, the cells were exposed at various concentrations such as 2.5, 25 and 50 microgram per ml. It was observed that the doping of Fe ions with cadmium selenide nanoparticles at low doses, that is 2.5 microgram per ml, can potentially kill the breast cancer cell lines than the other doses. It was found that they attach to the outer membrane of cancer cells due to the electrostatic interaction and they penetrate into the cancer cells. Conclusion. In the present work, cadmium selenide and Fe metal doped cadmium selenide samples with a stoichiometric ratio 5, 10 and 15% have been synthesized by chemical co-precipitation technique using mercaptan as a capping agent. As synthesized, 15% of Fe doped cadmium selenide nanoparticles shows 79% of enhanced photocatalytic activity under visible light compared to the pure cadmium selenide. As synthesized nanoparticles were clearly shown to follow pseudo first order kinetics. In addition, all synthesized nanoparticles were investigated against breast cancer cell lines and it was found to be inhibiting the cell growth by dose dependent inhibition. This paper was published in Material Science in Semiconductor Processing in the year of 2019. Chapter 4, Synthesis and Characterization of Manganese doped zinc selenide nanoparticles for photocatalytic activities and biological application. This is a synthesis procedure for the zinc selenide and manganese doped zinc selenide nanoparticles. Initially, 1:1 ratio of zinc sulfate solution is mixed with the sodium selenide. To this, hydrogen monohydrate was added drop by drop with constant stirring. After 15 minutes, a milky solution of zinc selenide was obtained. Then it's transferred to the 50 ml of autoclave. Then the reaction temperature was maintained at 170 degrees centigrade for 8 hours. Finally, the yellow colored of zinc selenide powder was obtained. Then it's washed several times using ethanol and water, then dried at 70 degrees centigrade. The procedure followed was same as in the synthesis of zinc selenide nanoparticles, and the appropriate ratio of manganese sulfate was dissolved in zinc sulfate solution. This slide shows the powder X-ray diffraction studies of zinc selenide and manganese doped zinc selenide nanoparticles. The high intense peaks obtained at 2 theta values corresponds to the plane of zinc selenide nanoparticles. It shows all the synthesized nanoparticles exhibit a site-like hexagonal structure, which is this data is matched with the JCPDS part number 000150105. The star symbol in this powder X-ray diffraction shows the incorporation of manganese ion into the zinc selenide, which is confirmed by the JCPDS code number 027030011. The ash symbol in the XRD data shows untreated selenium atoms in the zinc selenide nanoparticles, which can be removed many times using methanol and water. This slide shows a plot of strain and crystallized size versus manganese at zinc selenide nanoparticles. The crystallized size of zinc selenide nanoparticles was found to be 16.8 nanometer. By doping manganese into the zinc selenide nanoparticles, the crystallized size was found to be decreases from 16.8 to 8.3 with the increase of strain values, which can be calculated by plotting strain versus crystallized size with the as synthesized nanoparticles as shown in this slide. This slide shows HR-TEM and TEM-EDAS analysis for zinc selenide and manganese doped zinc selenide nanoparticles. Figure A shows all the samples exhibit spherical in shape and the particles were randomly distributed. Figure B, small a and b shows selected area of electron diffraction pattern shows sharp ring with several spots representing all the synthesized nanoparticles exhibit a polycrystalline in nature. This data is well agreement with the powder XRD. Figure C and D shows TEM-EDAS analysis of a synthesized compound which confirms the presence of zinc, selenium and manganese and to know its weight percentage of its composition. This slide shows the FT-IR spectra for zinc selenide and manganese doped zinc selenide nanoparticles in the range of 400 to 4000 centimeter power of -1. The broad peak at 3428 to 3434 4 centimeter power of -1 was assigned to the OA stretching vibration mode of zinc selenide nanoparticles. Then the peak at 473 and 628 centimeter power of -1 was due to the zinc selenide symmetric stretching and bending vibration mode of nanoparticles. Then the characteristics peak at 2931 centimeter power of -1 is due to the NS2 stretching vibration mode of synthesized nanoparticles. It indicates the interaction of N2H4 molecules existing in the compound. This slide shows the micro-Raman spectra of zinc selenide and manganese doped zinc selenide nanoparticles from 100 to the 600 centimeter power of -1. The Raman peaks at 236 centimeter power of -1 and 457 centimeter power of -1 was assigned to the 1 longitudinal and 2 longitudinal optical phonon mode of synthesized nanoparticles, and the characteristics peak at 234 centimeter power of -1 was assigned to the second transverse acoustic phonon mode of synthesized compounds. The 1 longitudinal optical phonon modes shift towards the lower frequency region as shown in figure B. This due to the smaller in particle size and higher surface area. This slide shows the UV absorbance and KM plot for zinc selenide and manganese doped zinc selenide nanoparticles. Here the absorbance was decreases by doping manganese ion into the zinc selenide nanoparticles, which reliable for redshift. And also the band gap values was found to be 2.59 electron volt for zinc selenide, and there was a small increase in band gap values are found from 2.63 electron volt to the 2.67 electron volt when the manganese ion incorporation into the zinc selenide nanoparticles, which is shown in the insert figure of absorbance spectra. This slide shows vibrating sample magnetometer. Pure zinc selenide nanoparticles shown weak ferromagnetic behavior, and the saturation magnetization values was found to be 2.92 in 10 power of -4 when the manganese ion incorporation into the zinc selenide nanoparticles. The MS loops or increases, so that the saturation magnetization values was increases. As a result, ferromagnetism that appears within a well-defined hysteresis loop that resulted with the exchange pairs among the Mn2 plus ion within the lattice of zinc selenide. This slide shows a UV absorbance spectra of zinc selenide and manganese doped zinc selenide nanoparticles using reactive black Y is an anionic dye. From 0 minutes to the 240 minutes when visible light UVA light is used. When UVA light is passed through the zinc selenide nanoparticles, the intensity of the light is increase, absorbance decreases with an increase of irradiation time. The maximum absorption wavelength for the RB5 dye was found to be 597 nanometer. The degradation efficiency of an azo dye were 36% for zinc selenide, 41, 68, 83% for 5, 10, and 15% of manganese doped zinc selenide nanoparticles respectively. As a result, 15% of manganese doped zinc selenide nanoparticles showed enhanced photocatalytic activity than pure zinc selenide, which is confirmed by plotting C/C0 versus time in minute power of -1 as shown in figure A. Figure B shows kinetic plot of zinc selenide and manganese doped zinc selenide nanoparticles. A straight line shows all the synthesized nanoparticles exhibit pseudo first order kinetics. The apparent rate constant values for zinc selenide is found to be 0.00514 minute power of -1, 0.00575, 0.00868, 0.0191 minute power of -1 for 5, 10, and 15% of manganese doped zinc selenide nanoparticles respectively. This slide shows the anti-cancer activity of zinc selenide and manganese doped zinc selenide nanoparticles on lung cancer cell lines. Initially, the cells were exposed at various concentrations such as 25, 50, and 75% of microgram per ml. Zinc selenide alone exposes to lung cancer cell line shows poor cytotoxicity. When the manganese ion incorporation into the zinc selenide nanoparticles, it shows a higher toxicity on lung cancer cell lines. It was observed that A54 cells decreased progressively at a low dosage from zinc selenide to 15% of manganese at zinc selenide nanoparticles. It was found that all the three samples, that is manganese doped zinc selenide nanoparticles at a low at a 75% of concentration shows substantial cytotoxicity than other samples. Conclusion: the nanoparticles of zinc selenide and manganese doped zinc selenide nanoparticles with a stoichiometric ratio of 5, 10, and 15% have been synthesized by hydrothermal method using hydrogen monohydrate as a reducing agent. The magnetic properties of as synthesized nanoparticles have been measured with the help of BSM. As a result, pure zinc selenide has shown weak ferromagnetic behavior, and the hysteresis loops curves increases with the addition of manganese ion incorporation into the zinc selenide nanoparticles. As synthesized, 15% of manganese at zinc selenide nanoparticles shows enhanced photocatalytic activity. That is, 83% of enhanced photocatalytic efficiency was observed at 15% of manganese at zinc selenide nanoparticles by using RB5 dye under UVA irradiation when compared to the zinc selenide. And all the synthesized nanoparticles obey to follow pseudo first order kinetics. Additionally, the cytotoxicity studies reveals that the incorporation of manganese into the zinc selenide nanoparticles established strong anti-proliferative activities than pure zinc selenide on lung cancer cell lines. Chapter 5, synthesis of pH-dependent TiO2 nanoparticles for bacterial growth inhibition and osteoblast proliferation. This synthesis procedure for TiO2 nanoparticles at various pH such as 6, 8, and 10 by sol gel technique. Initially, 1 ml of titanium tetraisopropoxide was mixed with the 9 ml of 2-propanol, then stirred for 6 hours. The resultant white sol is obtained, is dried for 130 degrees centigrade for 8 hours. Finally, the yellow crystal of titanium dioxide nanoparticles was obtained, is washed and centrifuged using ethanol and water. This slide shows the powder X-ray diffraction studies of TiO2 nanoparticles at various pH levels. The high intense peak at 2 theta values 25.5, 38, 48, 8.2, 53.9, 54.8, 63.1, 68.9, 70.3, 75.1 corresponds to the tetragonal alloy space of TiO2 nanoparticles. Likewise, low intensity peak at 2 theta values equal to the 30.8. The corresponding plane of 1 to 1 shows orthorhombic Bruchite phase. As a result, as synthesized nanoparticles shows high crystalline anatase phase with a small amount of Bruchite phase. In addition, the crystalline size of TiO2 nanoparticles was found to be 7.3 nanometer. When the pH values increases into the TiO2 nanoparticles, the crystalline size was increased from 7.23 to 16.8. So the average crystalline size of synthesized nanoparticles was found to in between 7 to 17, which can be found by plotting average crystalline size with the strain values versus as synthesized nanoparticles as shown in this slide. This slide shows the 10 analysis of TiO2 nanoparticles at various pH levels. This slide shows transmission electron microscopic images of a synthesized nanoparticle, shows spherical in shape and the particles were agglomerated with a uniform size distribution. This slide shows HR-10 images of synthesized nanoparticles. The d-spacing values are were found to be d-spacing values for anatase is 0.354 nanometer, 0.343 nanometer, 0.321 nanometer, and 0.285 nanometer for anatase, and 0.34 to 0.1314 and 0.306 and 0.274 nanometer for a Bruchite phase, which is well agreement with the powder XRT data. This slide shows a 10 MEDAX analysis of a synthesized compounds, which confirms the presence of titanium and oxygen. This slide shows FTIR spectra of TiO2 nanoparticles at various pH levels. The broad band in between 3,398 to 3,482 centimeter power of -1 was due to the OH stretching vibration mode of TiO2 nanoparticles. Then the characteristics peaks at 2009-20 and 2008-56 centimeter power of -1 was due to the symmetric and asymmetric stretching vibration mode of CS2 and CS3 respectively. Then the characteristics peak at 1006 30 centimeter power of -1 was due to the C double bond of stretching vibration mode of isopropyl alcohol. Then the peak at 638 to 652 centimeter power of -1 was due to the titanium oxygen titanium stretching mode of vibration. This slide shows a micro-Raman spectra of TiO2 nanoparticles at various pH levels. The anatase phase was observed at 145 and 196, 398, 156, 516, 519, and 640 centimeter power of -1. Likewise, the Brookite phase were observed at 247, 325 and 368 centimeter power of -1, which is shown the inside figure of micro-Raman spectra. This data is well agreement with the powder XRD experiment. This slide shows optical absorption spectra for TiO2 nanoparticles at various pH levels. The absorbance were observed near the visible region. This is due to the charge transfer from valence band to the conduction band. Then figure B shows the Kubelka-Monk plot of titanium dioxide nanoparticles at various pH. The band gap values for titanium dioxide were found to be 3.4 electron volt. When the pH values increases, the band gap values are found to be decreases from 3.33 electron volt to the 3.15 electron volt, which is shown in figure B. This slide shows the photoluminescence spectral studies. The rate of formation of electron hole pair can be separated, can be studied by using a PL spectral analysis. The broad band in between 520 to 540 nanometer was observed due to the agglomerator of TiO2 nanoparticles. There was 2 humps were observed at 114 nanometer and 542 nanometer. This due to the mixed phase of anatase and the Brookite. It was observed that the PL intensity of a TiO2 nano-size TiO2 was decreased than the TiO2 nanoparticle synthesis at pH 10. This is due to the TiO2 nanoparticles significantly reduces the electron hole pair separation and enhance the photocatalytic activity. This slide shows the effect of pH on degradation of reactive black azophide. Figure A shows a photocatalytic degradation of titanium dioxide nanoparticles by using RB5, this is an anionic dye, within 45 minutes. When the UVA light irradiated on the titanium dioxide nanoparticles, 96% of photocatalytic efficiency was observed. Figure B, we carried out control conditions in the presence of and absence of UV light with TiO2 nanoparticles as shown in figure B. In the presence of UV light shows 96% of photocatalytic efficiency, but in the absence of UV light shows only 16% of photocatalytic activity, which is shown in figure B. Then figure C. These are the A and B shows the controlled experiment with the dye on its own. C, D and E depicts the UV absorbance spectra for synthesized TiO2 nanoparticles by varying 6, 8 and 10 respectively as a result of TiO2 nanoparticles synthesis at pH 6 shows enhanced photocatalytic activity than 8 and 10. This slide shows all the synthesized nanoparticles exhibit pseudo first order kinetics. In this slide, you can see that the effect of TiO2 nanoparticle synthesis by varying pH on E. coli cell growth inhibition. Generally, the bacterial growth inhibition can be determined by FACS analysis, the flow cytometer analysis. A flow cytometry is a technique is used in eukaryotic cell to determine the cell viability and metabolism of synthesized nanoparticles. Figure A to E represents a dot plot of flow cytometry analysis with the side scatter light and forward scatter light. From the histogram, it was observed that there is a statistical increase in E. coli cell incorporation, that is 17.3% of incorporation were observed at TiO2 nanoparticle synthesis at pH 6 in the concentration of 200 microgram per ml. This is due to the smaller particle size exhibit higher inhibitory activity. The same result was observed by Bacillus subtilis on cell growth inhibition, that is almost 24 and 25% of cell incorporation were observed when the titanium dioxide nanoparticle synthesis at pH 6 at the concentration of 200 and 300 microgram per ml. This shows in the histogram of figure F. This slide shows the effect of TiO2 synthesis by varying pH on mouse mesenchymal stem cell. Figure A shows the MTT cell viability. Figure B represents BRD cell proliferation assay. Initially, the cells were exposed here, 3 different doses such as 25, 50, and 75 microgram per ml. It was observed that the cells were treated with the TiO2 nanoparticles at a different pH. There was a significant decrease in all the groups except the groups treated with the 75 microgram of TiO2 nanoparticle synthesis at pH 6 when compared to the control, as shown in figure A. In figure B, it was observed that high proliferation was observed in the groups treated with the TiO2 at pH 6 when compared to the other groups, as shown in figure B. It was observed that the TiO2 nanoparticle synthesis at pH 6 enhances cell proliferation assay, cell proliferation, and so they felicitate to the bone formation at a defective site. This paper was published in AAP Advances in the year of 2020. Conclusion: the photocatalytic activity of TiO2 nanoparticles has dye removal of 96% dye degraded within 45 minutes by using RB5 dye. And the photocatalytic activity of TiO2 nanoparticles will increase if the reaction performed in acidic condition. Also, the synthesis TiO2 nanoparticles obey to follow pseudo first order kinetics. Interestingly, TiO2 nanoparticle synthesis at pH 6 can be used at the medical implant. Minimal cytotoxicity against osteoblast cells indicates the synthesized nanoparticles could not affect the osteoblast cells if used as a bone implant. It could increase the proliferation of osteoblast, which has required for bone formation. Summary and future work. Chapter 1, introduction about the transition metal chalcogenides such as cadmium selenide, zinc selenide, and TiO2 nanoparticles. Chapter 2, materials and method. Chapter 3, a soft chemical co-precipitation method was employed for the preparation of cadmium selenide and Fe-doped cadmium selenide nanoparticles. The enhanced photocatalytic activity, that is 79% of enhanced photocatalytic activity was observed, and it acts as a good anti-cancer activity on breast cancer cell lines at a minimum dosage was observed on 15% of Fe metal doped at cadmium selenide nanoparticles. In chapter 4, the zinc selenide and manganese doped zinc selenide nanoparticles were synthesized by hydrothermal method. The enhanced photocatalytic activity, that means 82% of enhanced photocatalytic activity were observed when 15% of manganese incorporated into the zinc selenide has been noticed on 15% of Mn at zinc selenide nanoparticles when compared to the pure zinc selenide. In chapter 5, TiO2 nanoparticles have been prepared through sol-gel method by varying temperature, by varying pH values such as 6, 8, and 10. Enhanced photocatalytic activities was observed, that is 96% was observed with an anionic dye RB5 dye on synthesized TiO2 nanoparticles. Also, TiO2 nanoparticle synthesis at pH 6 can be used as a potential bacterial growth inhibitor and could be coated in medical implants to avoid inflammations. Future work. In addition to the present degradation studies, suitable transition dopant can be chosen in cadmium selenide, zinc selenide, and TiO2 for photocatalytic degradation with a recycling experiment for various dyes such as cargo red, methyl orange, methyl red, rhodamine blue with a different catalyst dosage analyzed. These are the list of my publications. These are the references I followed. These are the list of national and international conference and workshop I attended during my research period from 2017 to 2021. Acknowledgement. First, I thank my guide, Dr. E. Sundaravadivel sir, for his constant motivation, support, and guidance. I sincerely thank my DC member, Professor G. Shekhar sir, IIT Madras, and Professor M. Arivanandam sir, Anna University. I also thank external CV member, Professor P. Prabhu sir, Madras University. I would like to express my thank to Professor C. Muthamil Silvan sir, VC of ENT, and Professor D. John Trivadigal sir, Chairperson of Applied Sciences, SRM IST. I express my gratitude to Professor Napoleon sir, Dean Research, for their moral support. I wish to express my warm gratitude to Professor Arthanarishwari ma'am, head of the department. Also, I thank my Dr. M. Sasidharan sir, head of research in the department of SRM IST. I would like to thank SRM IST for their fellowship and computational facility and their instrumentation facility centers to pursue my PhD. I thank my family members for supporting me day in and day out. Finally, I thank all research scholars of chemistry, physics, and biotech friends for helping me regarding research activities. Once again, I thank my guide, Dr. E. Sundaravadivel sir, Dr. V. Ramesh sir, Dr. Suresh Perumal sir, Dr. Ramya ma'am, Dr. Sivaramakrishnan sir, and Kanagaraj sir will give moral support and guidance. Thank you so much, sir.
Now the question session, it's opened. Sir, Anbalavan sir, Vijayan sir, please take
Yes.
time.
So Vijayan sir.
Sir, நீங்க முடிச்சிருங்க sir. You can proceed, then after that I will take over, sir.
Okay.
Yes, yes.
Okay. Sridevi, you presented in a nice manner, and then the slides
Thank
are
you, sir.
also good.
Thank you, sir.
Okay. I want some clarification. You go to
Yes,
slide number 20.
One second, sir.
So first, I think in the third.
Yes, sir. Yes, sir. This slide, sir?
Yes.
Yes, sir.
So the block 1, cadmium selenide nanoparticle. You was in the
Yes, sir.
slide.
Yes.
So it agrees with your JCPDS value, no?
Yes, sir.
Then when the concentration of ion is increased to 5%, these
Yes,
two peaks merged into one and appears as a broad peak,
Yes, sir.
right?
Yes, sir. Yes, sir.
Then how can you say that the sample is the cadmium selenide?
Sir, actually, all the synthesis nanoparticles exhibit in amorphous in nature. Broadening of peaks is observed.
Yeah, that I know.
Mm.
But these two peaks are the characteristic peaks of cadmium selenide, you know.
Due to the Fe ions incorporated into the cadmium selenide, the peaks are disappear, sir. But pure informed two peaks.
If so, there is any changes in structure or the ABC value?
No, sir. But it's confirmed in SAID patterns, sir. The rings are not obtained in when Fe doped into the cadmium selenide nanoparticles, sir. For pure cadmium selenide, sharp rings were observed, sir. But in Fe doped into cadmium selenide nanoparticles, the second and third rings are not shown clearly, sir.
Oh. Have you calculated the ABC value for this pure and iron doped one?
Yes, sir.
Then only we can come to the conclusion. Right?
ABC
Because
what?
when you for 5% ion concentration
Yes, sir.
and 10% ion concentration, they both 220 and 311 merged and appears as a broad peak.
Yeah, yes, sir.
Oh.
Yes.
Suppose if the peaks are broad, then no problem.
Okay, sir.
They are merged into one. That is my question. Okay.
Okay.
Then you go to 21, slide number 21.
Yes, sir.
I think I want to some clarification about the EDX value,
Yes, sir.
but it is not visible.
Yes.
Okay. Actually, can increase little bit. Yeah. So I think the part of the portion is not visible. Yeah, okay, that's okay. Good. See this one,
Yes.
the first one, this is 5%,
Yes.
and the 10% and 15%.
15%. Okay.
The atomic percent of the atomic percent, how this, see there is a variation for 5%, 18.93%.
Yes, sir. For 10% is 16.1.
Suddenly there is a drop.
Yes, yes.
So you increase the ion concentration to
Concentration.
10%.
Yes, yes. It also increases in atomic
What is
weight
the reason? What is
percentage.
the reason? But in the third one, 15%, it is increases to 59.5.
52.9. Yes, sir.
Yeah, 52.9.
Yes.
Have you noticed, and what is the reason?
I don't know, sir, but I doped in 5, 10, and 15 weight percentage of Fe doped cadmium cylinder nanoparticles. But the from the data, the weight percentage of Fe doped is shown in 18 and 16 and 52.9, sir.
Please check. Right.
Yes.
And then
From the
22.
sir,
Line number
slide
22.
1 second, sir. 22, yes, sir.
Line number 22.
Yes, sir. 22.
Yeah, this is regarding your band gap. What
Yes,
is your
sir.
expectation, whether we need increased wide band gap or narrow band gap?
Narrow band gap, sir. Band gap values are decreased, sir, by doping Fe ions into the cadmium cylinder nanoparticle.
Yeah, and that is the result you have obtained here.
Yeah, yes, yes.
But my question is, what is your expectation? What is your for the good photocatalytic activities? Whether they what about the band gap? Whether the band gap will be narrow or wide?
Narrow, sir.
Narrow.
Narrow, oh, yes.
Why I'm asking is, when manganese dope,
Yes.
the dopant concentration increases, the band gap also increases.
Yes, sir.
But here the dopant concentration increases, the band gap decreases.
Yes, 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 sir.
What is your expectation? That is why I'm asking. Whether you want to increase the band gap or decrease the band gap. Otherwise, whatever the band gap, we are studying the photocatalytic activity.
No, sir. Actually, photocatalytic efficiency, I am not depend upon these band gap values. I depends on the particle size, sir. Actually,
Okay.
particle size. The crystal size is decreases. The band gap, the photocatalytic efficiency was increased. In addition to that, biological activities also increase if the particle size is too low.
So there is no
Two sides.
relation between band gap and photocatalytic activities.
Here, no idea, sir. No relationship between band gap and efficiency, sir. Relationship only the size, crystal size with charge carriers, then photocatalytic activity, sir.
Okay, and we go to slide number 26.
Yes, sir. Yes.
Yes. What is this K value?
K value is 0.0136, sir.
Now,
It's a rate constant.
what is K value? A rate constant or some?
Rate constant value, sir. Rate constant, sir. For CDSA, it can be determined from 2.303, the slopes, the 2.303 into K value, sir. Slope value, sir.
No. here also,
Yes, sir.
there is no definite relationship between the rate constant and the dopant concentration. See, for the first one, 0.0176 for 5%, I think. This is
No,
for
sir.
10%. Second one is 10%. And the third
No,
one
sir.
is
First one for CDSC, sir. 0.0136, sir, for CDSC. 0.0176, sir, 5. Then 0.212, 10. 0.0207 for 15%.
yeah, there is a 15%. There is a decrease in rate constant.
Yes, sir.
Oh,
Yes,
What is
here
it?
also the R square values is decreased, sir. 0.8219.
R square value.
R square value is around 0.9, which emphasizes all the synthesis nanoparticles who raise to pseudo first order kinetics, sir.
Hmm.
Yes, sir. It may be in the 0.858999.5 like this, sir. In the range of,
Okay. Then you go to slide number 32.
yes, sir. Yes, sir.
See the JCPDS pattern is for nanoparticle or bulk material.
Nanoparticles, sir. Bulks, I'm sorry, bulk materials, sir. Zinc cell bulk materials, sir. Yes, already reported. Yes, sir. Reported.
There is no exact match between these JCPDS value and the one, because the see here
Hmm.
the intensity of the peaks, all the three peaks, the first three peaks will be higher.
Yes, sir.
But in
Yes,
this case, in the case of your synthesized material, it is the first and the third is very, very low.
Yes, sir.
So that may be because of this, we are comparing the bulk and nano.
Yes, sir.
And 38. This is the title, Vibrating Sample Magnetometer Studies.
Yes, sir.
It's not vibrating sample magnetometer study. Vibrating sample magnetometer is a device or instrument which is used to study the magnetic behavior.
Okay, sir.
Okay,
Okay,
that is
sir.
an instrument.
Okay, sir. Yes, sir.
Right? The magnetic studies.
Okay, sir.
Like that you can write.
Okay,
This is
sir.
not a magnetic sample, vibrating sample magnetometer studies.
Okay, sir. I change.
Okay.
And correct. Yes.
And almost at this last slide number 52
Yes, sir.
regarding your photoluminescence spectrum.
Yes, yes. One second, sir. Yes, sir.
What is the excitation wavelength?
This one, sir. 633, sir. I used 633 nanometers, sir, for PL spectral studies.
You are not mentioned here. And how will you fix that 633 nanometer as an excitation wavelength?
But I already used 323 nanometer. The peaks is not appeared clearly, sir. Then I moved to the 633 nanometer. The broadened peaks obtained in the range of 100 to 700 nanometers, sir. The peak is not obtained low wavelength, sir. That's
And normally, how do you
300.
fix the excitation wavelength?
633,
Select the
sir.
excitation
I
wavelength
used
for this normal procedure.
I don't know, sir.
So you go to The cutoff wavelength of our UV visible spectrum will be the excitation wavelength for photoluminescence spectrum. Am I correct?
It's 400 to 800.
Okay, 146, 46.
Yes. Yes.
Yes. No, previous one. Almost the lattice constant A
Yes. Sir.
is almost same.
Yes, sir. Almost same. Sir. I got almost same.
Both
3.7.
the A and
There is no
B
change.
are almost same.
Yes, sir.
And also that means without changing the lattice parameter value, you are changing only the
pH.
pH value.
Yes, sir.
So while changing the pH value, there is no structural change.
Yes, sir. No variations of structure I didn't, sir.
Okay. And finally, your intention is to study photocatalytic activities and antimicrobial studies.
Yes, sir. Yes, sir.
Okay, then what is the need of go for magnetic measurements?
Oh, sir. Go for
Magnetic measurements.
magnetic measurements.
அது எதுக்கு பண்ணிருக்கீங்கன்ற உங்களோட இன்டென்ஷன் வந்து photocatalytic activities antimicrobial இதுதான்.
Yes, sir. But in this topic, I didn't do the magnetic studies, sir. Only cadmium selenide and zinc selenide nanoparticles.
Leave this chapter, but the
Yes.
other materials.
Okay, sir.
Okay. Okay, good. I will. Sir. Vijay,
sir. Yes, sir. Yes, sir.
You can proceed, sir. You can proceed, sir.
Okay. Ms. Sridevi,
Sir, good morning,
I
sir.
am audible to you.
Yes, sir. Yes, sir.
Yeah. So first of all, let me congratulate you for your nice presentation
Thank you, sir.
and the systematic studies, right?
Yes, sir. Yes, sir. Yes, sir.
Even though I have sent my separate report to SRM University,
Okay, sir.
and based on that, they have constituted a committee.
Okay.
And anyway, you are facing today's PhD BioVoS examination. Based on
Yes,
your
sir.
presentation, I need some queries.
Okay.
Mainly, you have taken TiO2 nanoparticles, right? And then
Yes, sir.
cadmium selenide, zinc selenide with the different dopants,
Yes.
manganese, iron, something like that, right?
Yes, yes, sir.
So I need a few clarifications.
Yes, sir.
First of all, you have taken a co-precipitation method.
Yes, sir.
After that, you adopted the hydrothermal method for making zinc selenide,
Yes, sir.
right? And then TiO2 nanoparticles, you made a sol gel method, right?
Yes, yes, yes.
Yeah. So the three different methods you adopted, right?
Yes, sir. Yes, sir.
For making three different types of materials.
Yes, technical methods I used, sir. Three different
So,
methods.
what is your main aim by keeping some idea, right? For
Yes,
what
sir.
application? Mainly, you are mentioning that some biomedical applications,
Yeah.
right?
Yes,
All
sir.
materials are showing the biomedical application,
Yes, sir.
or only few materials. How you come to a conclusion? You are having any collaboration with the medical institute?
Yes,
How
sir,
you are
yes, sir.
proposing this type of applications?
Actually, I'm collaborate with the SRM biotech faculty members, Dr. Sridevi ma'am and Dr. Kanagaras sir, Dr. Shivaraman sir. Both are done in anti-cancer activities and antibacterial growth inhibition for my synthesis samples, sir.
Okay. And then your material, have you attempted for analysis or checking purpose, or how you are exposing or how you are proposing that applications?
Yes, sir. Actually, I analyzed only, sir. But in future work, I'm going to the some devices, sir, like a bone implant, then a teeth implant like this, sir.
Okay, so
This
some
is my
implantation
future work, sir.
purpose
Yes, yes, yes.
you are also planning in the future, right?
Yes, yes, yes.
Okay,
sir.
that's good. And another one, particularly for your cadmium
Yes.
selenide co-precipitation method,
Yes,
you
sir.
have taken 5% Fe, 10% Fe, 15% Fe, right?
Yes, sir.
And you increase it to 5%. So what is your main objective?
Yes,
And
sir.
why not 3, 4, 5, 6, something like that? What is your main objective for keeping this 5, 10, 15?
Okay, sir.
Almost for all the other materials also you are keeping the same percentage, right?
Yes, 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 sir.
Yeah. So how you come to a conclusion? Have you done any trial and error experiments? Or how you are proposing this type of percentage, weight percentage?
So already reported 3, 5, then 7 in cadmium selenide doped, doped cadmium selenide nanoparticles. So I tried 5, 10, and 15%. And one of the literatures they shown incorporation of ion into the cadmium selenide nanoparticles shows enhanced photocatalytic activity. So that I tried in the 15 maximum amount of Fe doped into the cadmium selenide nanoparticles. This is a toxic one. Then I follow less toxic and non-toxic of T like this.
But how you are ensuring that 5%, 10% has gone inside the crystalline matrix?
Yes.
You are showing some XRD graph, that is fine. But in addition to that, how you are ensuring your chemical composition wise it has gone inside? I am
Yes.
saying that 10% you are presenting here, and just I am expecting that it has not gone 10. It has gone only 3. How you justify? How you justify? Madam, Ramya Devi, you are talking?
Yes.
No, somebody is in between. Maybe they are giving answer or I don't know.
I muted,
So,
sir.
Madam
I
Ramya
muted.
Devi.
Yeah, so you got me what I am asking.
Yeah, understood, sir, but I sorry, sir.
No. For example, you have taken 5% Fe doped, right?
Yes, sir.
And 10% you mentioned, and then 15%, right?
Yes, sir. Yes, sir.
So how you are ensuring that 5% it has gone inside or 10% it has gone inside?
From TEM redox analysis, we from the atomic weight of weight percentage, we conclude this one. But
Can you go to your slide number 21?
yes, sir. Yes, sir.
Yeah, but here if you see, you mentioned that 5%, 10%, 15%, right?
Yes, sir. Atomic weight. Yes.
Yeah. But have you identified all the peaks?
Yes, sir. Identify all the peaks, sir. Five and 10, 15%. The peaks is not up. Secondary peaks is not appearing, sir.
Okay.
The peak 42 and 49.7 peaks not obtained when Fe ions incorporation into the cadmium selenide nanoparticles.
Can you go to your slide number 48? Again, another EDS.
Okay, sir. Yes, sir. Okay, the weight composition I not mentioned.
Here also you are getting all the titanium oxide peaks.
Oh, sir. Yes, sir.
with what all the percentage you have taken, it is exactly it is coming, or it is any variation is there?
Slight variation is there, sir, but I didn't mention. I mentioned in paper, sir. I didn't mention here. Sorry, sir. Slight variation is observed, sir.
What is the purity of your materials?
99.9, sir. Titanium
Nine?
tetra sir. 99.9% of titanium tetra isopropoxide mixed with the 2-propanol, sir. 2-propanol solution.
Okay. And again, in the another case also, you have taken cadmium selenide, again you have taken 5, 10, 15, right? And
Yes,
zinc selenide also, Mn also you have taken 5, 10, 15.
Yes, yes, sir.
But
Yes.
why? I am asking, in the literature you found this value, or what? How you come to a conclusion?
From the literature survey already, they are used a minimum dopant concentration, so that I tried maximum concentration from 5, 10, 15% by studying various applications and the characterization like this.
But for example, if you are increasing your dopant percentage, for what applications the material is behavior is good?
Yes, sir. If the dopant ion concentration increases, the photocatalytic activities and the biological applications also increases, sir. It shows only the maximum percentage of efficiency obtained at maximum percentage. For example, if we do cadmium selenide 15% shows enhanced photocatalytic activity and anti-cancer activity, sir.
Okay. But you yourself, you mentioned that already it is having some literature report.
Yes,
And what
sir.
is your novelty from your observation?
Already I didn't do this applications, sensors, solar cells like this they done, sir. But I'm trying to studying these applications, photocatalytic activities and biological applications. These are
But
the
already
applications
in the reported literature, then what
Yes.
purpose they have reported in the literature? For what applications they have reported, and what is your you mentioned that photocatalytic activity application you mentioned. And already report
yes.
literature, in what application they have reported? In what basis they reported that material?
Sensor, solar cells, like this, sir.
Okay, because whenever you are reporting the same material, and at least your aim and then your objective should be different, right?
Yes.
And then try to make
Yes.
some devices. Then only you can able to show some product for the societal purpose, right?
Okay, sir. Okay, sir.
And one more
Okay,
thing,
sir.
and you changed in titanium oxide some pH values, right?
Yes, sir. Yes, sir.
And the pure titanium oxide, you mentioned that 7.3 crystallite size.
Yes, yes, sir. Yes,
And
sir.
for 6, 10, 6, 8, and then 10, right?
Yes, sir.
And I have seen your values are exactly increasing by 3. Can you take
Yes,
that slide? Can you go? Can you open that slide? The value you have given, crystallite
yes,
size,
sir.
tabular
Yes,
column.
sir.
Yeah.
Yeah.
I have seen pure titanium oxide nanoparticles, it is 7, right?
Yes, sir.
And whenever you are increasing the pH, again 3 is increasing 10. And
Yes.
again it is increasing 3, 13. And again it is increasing 3.
Yes.
How it is periodically increasing? Whether that is a correct way, or you are getting the correct calculation, in which method you calculated the crystallite size?
Scalar formula, sir.
What is the Scalar formula?
0.94 into lambda by beta cos theta, sir.
What is beta?
Beta is the angle, sir.
That is full width of maximum.
Yes, FW is the full width
Okay.
of maximum.
What is lambda?
Lambda is the wavelength, sir.
Wavelength of
X-ray, sir.
X-ray.
Yes, sir.
So in your case, what is the value you have taken?
I don't understand, sir.
No. Lambda, you have taken some value, right? Wavelength you are telling, X-ray you are telling, right?
Yes, yes.
What is the
Yes,
value?
sir.
What is the value?
What's the value of lambda, right, sir? 1.54, sir.
Which which target? Which source you have taken? Copper K alpha or molybdenum K alpha?
Sir. Copper K alpha, sir. Copper K alpha, sir.
Okay.
Sir.
And now you can see the
powder
values.
XR, sir.
Yeah, powder XRD. Yeah, right.
Yes, sir.
And you can see the crystallite size, how it is periodically increasing. 7, 10, 13, 16. That is the calculated values, or How you are getting exactly the similar results with the variation of 3?
I calculated this from a debased Carrel formula. Then only I show that and plotted from average crystallization with the strain values versus synthesis nanoparticles.
Because your strain is not that much, right? It is other pure in comparison with the others pH values. It is not having that much strain, but even your crystallite size is having different in values, right?
Okay.
So this you can check again.
Okay, sir.
With your calculations.
Okay, sir. I will check
Right?
again, sir. Yes,
and
sir.
then slide number 20.
Yes, sir.
Yeah, this is already Professor Anbalagan sir has discussed it clearly.
Yes, sir.
And here my question is, whenever you are increasing the percentage, right? 5 and then
Yes.
10 and then 15, right?
Yes, sir. Yes, sir.
But anyway, 5 and then 10, okay, 5 is okay. And then 10, some peaks are appearing, right?
Yes, sir. 10, not 15, sir. 15, some
yeah,
peaks are appearing.
15,
Yes.
some peaks are appearing.
Yes.
Whether that HKL and then your original JCPDS HAL both are matching or any variation is there. What about its 2 theta values?
Sorry, sir. I don't know, sir.
Because whatever the peak is appearing, it is having slight variation in your 2 theta values. So you have to calculate
Yes, sir,
better
yes, sir.
this HKL values of 15, whether it is matching or not, right?
Oh, okay, sir.
Or is there is any phase change is there? So everything you have to clearly identify.
Oh.
Right?
Okay, sir.
And what about your stability of your material? For example, you prepared this maybe some 6 months before.
No, sir. I prepared this sample in 2019, sir.
2019. For example, if you are having this sample now,
yes, sir.
What about the stability? Can you do this XRD? You will get the same result.
No, sir. I didn't do, sir. But we'll check, sir. I didn't do, sir.
No.
Within
what is
1
your
month,
answer?
I take
Whether
a
the same result
characterization
will
and
come, or
application.
you will be getting
Surely same
other
result will come, sir. I know, sir. Surely same result will come, sir.
same result will come. That means stability is good.
Yes, sir. After 1 year, I'm going to take 1 day XRD of this CDSC. The same powder XRD results are appear, sir. From this, I
Okay, yeah, you can try. You can try, and then you can check your results. I mean that stability, right?
okay, sir. Now I'm trying.
What about your repeatability of your experiments? For example, you have done right. You reported in your literature, and then some journals are there.
Yes,
if I am following your method,
yes, sir.
the same result will come. What about your repeatability of your experiments?
Yes, sir. I repeat my experiment in triplicate, sir, for each applications one.
Okay. So it will come, right?
Yes, sir. It will come.
Okay. Okay. You so Sridevi, so you have done a wonderful work and then good bottom up work, but still you can improve your number of publications, right? And then you can concentrate some device. You can collaborate with some medical institutes.
Okay.
And then you can make some device out of your research. Then only we can able to say that some societal product I made it.
Okay, sir.
Right?
Okay, sir.
Then you can proudly say that from my research findings, I made some societal product.
Okay, sir. Okay, sir. Sure, sir.
Right?
Okay, sir. Yes, sir.
Sir, I am handing over. Sir, Sundaravadivel, sir, you can take over.
Yes.
Yes,
Yeah,
sir.
maybe we will ask questions from the audience.
Yes, sir. Yes, sir. Any question from audience? The scholars and professors who are on the online may get clarification or interact with the candidate now.
In audience, if you want any clarification, please let me know. For your suggestion also, it's welcome here. For scholar and other institute faculties.
So, Sridevi,
Sir,
yeah, it's a well presentation.
thank you.
The follow of the unblock answer questions, I have
Yes,
not
sir.
convinced your particle size and band gap. So, as you said, your particle size is increased, right? Your
Yes, sir.
crystallite size. So, but band gap, what about your band gap? When you
Crystalline
increase,
sizes increases, band gap values was a decreases, sir. So reverse of the inverse proportion, actually.
but
If
your
the
band gap is
crystal size
increasing,
increases,
right?
band
When
gap
you,
values.
but your band gap is increasing, right? When you load with these other metals.
Yes, sir.
Just opposite, right?
Uh,
As you
yes.
you discussed with Anbalagan sir. So
Okay, sir.
yeah, make sure when you go interview somewhere, just make sure with the literatures and other
Okay,
publishers.
sir.
Okay, is standard quality publishers.
Sure, sir.
And do you know what is the there is two different band gaps. Which band gap you have calculated?
Direct band gap, sir.
You calculated
Yes, sir.
direct band gap. Why you
Yes, sir.
calculated direct band gap? Do you have any idea?
For these are 2 to 6 type of semiconductor materials shown direct band gap values from the literature survey I found, and I follow direct band gap values. Set of semiconductor materials, so that I used direct band gap values by using
Okay.
Welcome relation.
Okay, so one more thing, in sunlight or solar light, the
Yes,
azo
sir.
dyes dye
Yes.
itself can absorb the light, as we know everyone.
Yes, sir.
Like different
Yeah.
colors can
Yes.
absorb different particular wavelength, right? So why you
Yes, yes.
choose for dye molecule for your photocatalytic study? Because we cannot compare with the catalytic efficiency when
Yes,
you add with the dye molecule. So the dye can absorb the sunlight and then it can react. So how did you confirm whether either your catalyst is involved in the reaction or dye is involved in the reaction?
At least is involved in this reaction, sir.
How we can confirm? Because dye itself auto degradation, right? When you put in
Yes.
the dye and kept it in the light, so it can
Yes,
decolorize, as we know everyone.
Yes.
So
Yes.
it's difficult
Yes,
to
yes, sir.
find, right? So that
Yes.
might be you need to make sure your answers when you go for your either interview or somewhere. And actually your way of, I mean, your different thesis. So you have chosen cadmium sulfide, selenide and zinc selenide, but why you choose titanium in the last chapter?
Sir, actually, first cadmium selenide is the toxic, sir. Then zinc selenide is the least toxic, then followed by the by comparative studies, toxic, least toxic, and non-toxic.
But we cannot compare titanium dioxide to selenide, right? Zinc selenide and
Yes.
cadmium sulfide.
Yes,
Then
yes, sir.
what is the correlation? Do you have any idea why you chosen particularly this titanium?
Yes, sir. This for all in biological applications, sir. You know, cadmium selenide itself used in cancer activities at low dose dependent, so that I used in cadmium selenide, zinc selenide for biological activities. In addition to that, TiO2 also it acts as a bone implant. That's why I choose these nanoparticles, sir.
Okay, maybe you can check later. You did not convince my things. And one more thing, your XRD spectra, actually you run too much fast your scan rate. So that is
Yes.
very hard to find your crystalline size and crystallite size. Do you
Yes.
know what is crystallite size and crystalline size? Is there any difference or is the same?
Crystallite size or particle size or crystalline size, sir? What do you say, sir? I don't know.
No, there is two things like you have mentioned crystallite size.
Yes, sir. Yes, sir.
Do you know crystalline size? What is there any difference or is the same?
It's a difference. Crystallite size from the XRD data, crystallite size can be determined from the scalar formula.
Okay.
Crystalline size is different. Sir.
How we can calculate that one?
Yes.
Do you know? How we can calculate crystalline
No,
size?
sorry, sir. I don't know. Sir. I only calculated crystalline size and the particle size, sir. Average crystalline size with the particle size, sir.
Okay. Okay. So when you do XRD, you need to make sure, Sridevi, okay, when you go on presentation somewhere in the interview, maybe it is useful for you. Okay. Thank you so much. Yeah.
Okay,
I
sir.
have done
Thank you
with
so
my
much.
comments.
Okay, sir. Thank you so much, sir.
Any other question from audience? If no more questions from audience, we will conclude the VIO's examination session now. Vijayan sir, shall we conclude now?
Vijayan sir.
Yes, sir. Yes, sir. Yeah, yes, sir. You can proceed,
Yes,
sir.
sir.
Underline, sir.
Yes, sir. Yes, sir.
Yes, sir. Yes, sir. Yeah.
All the audience will agree with us that the candidate Sridevi has presented the thesis in a nice manner with the support of the very good preparation or very good prepared the slides. And myself, the Professor Vijayan, and one of the audience, I think Dr. Sridevi, asked many questions with the candidate, and the candidate has answered almost all the questions satisfactorily. And during your presentation, he showed the number of papers published in the international reputed journal. So all these fulfills the criteria for the award of PhD degree as per the UGC guidelines. So with these permissions or with these observations and permissions from the authorities, the committee strongly recommend the candidate for the award of PhD degree from the SRM University. So the work is good work and social relevant, presented in a nice manner, and published in the required number of papers. So I feel proud to recommend the candidate for the award of PhD degree from the SRM University. Now, the Vijayan sir will continue.
Yeah, Sridevi. Yeah, you have done a wonderful work and then good presentation. So you can continue the similar motto, and then you can try to guide some good number of PhD students. But what are all the suggestions given by the examiners and then other members? So you can make a note, and then in future you can try to rectify those things. And in addition to that, we know that the difficulty for girl candidates. So you have done a lot of characterization from pillar to post. So once again, congratulations, and then congratulations to your guide also. He has done a wonderful job for guiding such a very good student. So congratulations, both of you.
Thank you, sir. Thank you very much. So, finally, I can conclude the audience and the examiner accepted for the award of the degree PhD to the TV Sridevi. So I can happily call TV Sridevi hereafter Dr. TV Sridevi. And finally, I திருவள்ளுவர் quote, ஆக்கமும் கேடும் அதனால் வருதலால் காத்து ஓம்பல் சொல்லின்கண் சோர்வு. So with this quote, I can conclude the meeting. Thank you very much to one and all attending the 5 hours examination. Thank you very much.